Hey everybody, hopefully you've already downloaded the notes-taking guide. You've either printed it out or downloaded it and you're ready to annotate it, or you can do the old-fashioned way and just write it out in your notebook. So a couple things to get started. In this lesson, our objective is that we're going to learn how to determine the domains and find the asymptotes, both vertical and horizontal, of rational functions. So a rational function basically is a function that looks like this form, where we have some function in the numerator and some function in the denominator. Okay, so rational, remember the root word is ratio or fraction, where it looks like that. Okay, and then a vertical asymptote is that it is a vertical line where f of x is undefined, or we can say that it's related to excluded values of the domain. So basically, wherever the f of x is undefined, which usually means we're looking at the values of the denominator, because we can't have an undefined denominator at equals 0. So that's where we're going to find that. And then the horizontal asymptote is defined as a horizontal line where f of x has no value at all. And usually we find this and we compare the degrees of the numerator, we usually call that n, and the denominator, we usually call that m, where let's do it this way. If the numerator is greater than the power of the numerator, or the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the numerator degree is is less than the degree of the denominator, we say the horizontal asymptote is at y equals 0. And if the numerator degree is equal to the degree of the denominator, we say the horizontal asymptote is at y equals the value of a over b, where a is the leading coefficient of the numerator and b is the leading coefficient on the denominator. And I'll show you what that looks like in a little bit. Okay, moving on, talking about rational functions, and you can read about this on page 142. The domain of a rational function of x includes all numbers except, and we're talking about it can't include values of x that make f of x undefined. Basically, that means any value of x where the denominator would equal 0. And to find the domain of a rational function of x, we're going to set the domain, or set the denominator equal to 0 and find the excluded values first. And we'll show you how to do that right now. So this is example 1. It says find the domain of the function f of x equals 1 over x squared minus 9. So going back up here, to find the domain, we're going to set the denominator equal to 0. So we're literally going to take this denominator, which is x squared minus 9, and we're going to set it equal to 0. We're going to solve this equation because I want to know what values for x would make the function on the denominator equal 0, which would give it an undefined value. So if I add 9 to both sides, we get x squared equals 9. Take the square root of both sides plus or minus, and I would get x equals plus or minus 3. So I know if x equals positive 3 or negative 3, then the value of f of x would be 1 over 0, which is a problem. It's undefined here. We can't have that. So we say x cannot equal plus or minus 3. So the domain, and now I'm going to show you what that means is, if this are my values for x, and here's negative 3 and here's positive 3, I know I cannot equal negative 3 and I cannot equal positive 3 because those values make the denominator equal to 0. So it can equal every other value. So the way that we say that for the domain is we'll say in interval notation that it can be anything from the left up to negative 3. So we'd call that negative infinity to negative 3. Don't end on negative 3. With or union from negative 3 to 3 in between here. Union, again, we're skipping over the value of 3, and it can be anything past the value of 3. If we're starting at 3 and going to positive infinity. So the domain is going to look like this, okay? The way you can say it in words is you would say all reals except x equals negative 3 and 3. Okay, and this is an interval notation, which is usually what we're going to use. Okay, let's talk about horizontal and vertical asymptotes, and you can read about this on page 143. So the notation f of x approaches 5 as x approaches infinity means that the line of y equals 5 is a horizontal asymptote of f. And you can actually read about this on page 143 in that box by the definition of a horizontal asymptote. So here's what we know. Let f be the rational function given by f of x equals the numerator function over the denominator function. It's two polynomials, okay? Remember we learned our definitions of polynomials. This is a definition of one polynomial. Here's the definition of the other. Where the numerator function and the denominator function have no common factors. If they have common factors, you have to cancel them out. But right now we're going to assume there's none. So the graph of f has vertical asymptotes at wherever the function on the denominator equals 0. Okay, aka where d of x, or I should say where f of x is undefined. Okay. And then looking at part 2, the graph of f has at most one horizontal determined by, and actually, hold on, I think this got split up. Here we go. Determined by, and this we're going to be looking at the degrees of the numerator, which is n of x, and of the denominator, which is d of x. So remember that the degree of the numerator, we call that n, and the degree of the denominator, we call that m. If the degree of the numerator is less than the degree of the denominator, we kind of talked about this in the definition, then the horizontal asymptote is at y equals 0. For any degree where the numerator is less than the degree of the denominator. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is at y equals the value of a over b, where A is the leading coefficient of the numerator function, and B is the leading coefficient of the function on the bottom. And if the numerator degree is bigger than the denominator degree, then the graph has no horizontal asymptote. So let's talk about how to find the asymptotes of the function, where we would call this the n of x, and this is the d of x. Okay, so let's look at the asymptote. So now there's two types of asymptotes. Remember, the vertical asymptote, we always look at the denominator, and we set it equal to 0. So we're going to set the denominator x squared minus x minus 6 equal to 0. And we're going to solve this. You can choose which way you want to solve. You could factor. You could use quadratic equation. This one seems really easy to factor, so that's what I'm going to do. I know x minus 3 and x plus 2 will multiply to a minus 6 and add to a negative x. And if I set each of those parentheses or factors equal to 0, I get x equals 3 and x equals negative 2. And that is my vertical asymptotes. Okay. For my horizontal asymptotes, I'm going to look at the degree of the denominator. So I know there's this invisible 1 on here, so I know my degree here is 1. And my degree on the denominator is 2. So if n, the degree here, is smaller than the degree on the bottom, if I look up here at my definition, if n is smaller than m, that's this case A, then I know my horizontal asymptote is at y equals 0. And let me show you what that would look like if you were to graph it. So if you were to graph this, and we were to graph our asymptotes, okay, so in purple I'm going to put my vertical asymptotes at 1, 2, 3. So there's this vertical asymptote at x equals 3 where the graph cannot go past through it. Okay, it literally doesn't have a value on it. Also at x equals negative 2. So those are my vertical asymptotes. And my horizontal asymptote is at y equals 0, which is right here. So those are my asymptotes. And the graph of f of x, we would pick values to kind of flesh out what it would look like. It could look something like this. Okay, it could look something like, whoops, it could look something like this, whoops. Okay, we're not sure what it looks like, but we do know it will not cross those asymptotes. The values of the function cannot cross these asymptotes. That's like a boundary for them. Okay, and then we won't go into it, but an example of asymptotic behavior that occurs in real life could be like the cost of laws that are passed that affect businesses. We call them regulations. So sometimes they say, you know, businesses have to reduce their pollutant output by a certain percentage. We could also say that a cost / benefit. So for those of you who are interested in going into business, a cost benefit model would also use asymptotes. So you would be using that because there's certain boundaries to costs and benefits as well.